originally empezó siendo my main thing, a lo que voy a Cleveland y todo esto, pues son cosas mucho menos mainstream, ¿no? Y me gustan porque es muy teórico, pero es también trabajar con datos y mucha estadística y tal. Pero luego pienso en proyección a proyectos chulos en el futuro, postdoc options y tal, y es mucho más narrow. Y hacer otro tipo de cosas me gusta también, pues por lo que estoy haciendo David, lo que voy a hablar aquí, que me parece como un poco de aire fresco, ¿no? De tocar otras cosas. Es verdad que todo lo que estoy haciendo sí que, bueno, you can think and they have something in common. Y la idea es saber si el PhD, puedo hacer un rap que sea coherente, una historia coherente. Pero eso no tengo muy claro cuál sería mi... O sea, por ejemplo, estoy en Euclid, estoy haciendo ahora con David, son cosas más de galaxies, esto es CMB. Entonces, o sea, todavía no tengo claro si quiero focus my attention on trying to put more papers out en X o Y o Z. Entonces, bueno, estoy todavía pensando, decidiendo, pero por ahora eso, o sea, contento porque los proyectos que estoy haciendo me motivan, me aprendo un montón, me parecen interesantes, no me aburre. En el Zoom.
Irati.
No, Irati me ha dicho que...
Diego, Josh.
You just send the reminder, so I guess that if, I guess we can start, and if anyone.
Sure.
Are they only joining online?
No problem.
Silvia had a doctor appointment, so she couldn't join.
Yeah, participants 5, I see here in Zoom.
So maybe.
There's some people connected.
Yeah. All right, so good morning. Today we have Mikel Martin from the Instituto de Física Teórica de Madrid, and he's going to explain a bit his work. So thank you for coming, and the floor is yours.
Thank you for your introduction. Good morning, everyone. Egunon, Dene. So yeah, as she said, I'm a PhD student at the Instituto de Física Teórica in Madrid. Well, I'd like to start by thanking Raul for not only giving me the opportunity and come talk to you, but also for giving me the opportunity 5 years ago to come here and do a 2-month internship back when I didn't even know what a power spectrum was. And now here I am talking about cosmology stuff. So here we go. So the topic for today's seminar is Hemispherical Power Asymmetry, Minkowski Functionals, and Gaussianity. This is not my main thing, okay? It's just a heads up. But I thought it would be something more interesting for you, hopefully. And hopefully there's things here that you can take away with you and are more useful for you, okay? So the work that I'm going to present here has been done in collaboration with these 2 people here, Javier and Joseba. Joseba was this master's student that originally kickstarted the project. Then he got offered a PhD in quantum cryptography. He left us, he went to make some money, and we carried on. And Javier is a postdoc at IFT working with us, okay? And I have to say, we are hoping to put this out in the archive, put it out in 2 weeks, 1 week, 2 weeks. So it's basically finalized, but some of the things that I might show are a bit preliminary. So I'm not so much interested in the technical details of the results and the conclusions and the nitty-gritty details. Hopefully it's a bit more, explain what we do, why we do it, how we do it, and then we can have some back and forth discussion that it's the thing that I'm looking forward to. Outline, quite simple. I'm going to spend some time actually, explaining the title, right? Because, the concept there might not be familiar to everyone. So I'll start by talking about what is hemispherical power asymmetry. Why do we care about it? Then I'll jump into the second part of the title, where it said Minkowski Functionals. Some of you might have worked with them. Some of you might not even know what they are. I think this is probably a place that you can take something home. And because now that we've entered the era of cosmology beyond 2-point statistics, this kind of tool is something interesting to have in your toolkit, in my opinion. And I think it's going to become more and more useful and relevant in the community. And then, of course, I'll just put the two things together and explain what we've done, how we've used these things to study these things, and what is it that we're finding. Okay? So let's start with the first point. What's hemispherical power asymmetry? So let me tell you how the story went. This is WMAP. Okay, this is the second ever full sky cosmic microwave background telescope that was launched. Okay, the first one was Kobe. That was the first spacecraft seeing anisotropies, perturbations in the cosmic microwave background, and they got the Nobel Prize. WMAP was the second, and with WMAP, we basically started, let's say, the era of precision cosmology, right? Because this is basically what WMAP saw, right? These are perturbations in the cosmic microwave background. Something that I always like to remind people that maybe don't work with the CMB so much, whenever you see an image like this is kind of fake, okay? You're always gonna have some background, some galaxy in there in all different frequencies. And how you go from here to there, that's a bit of magic. Well, not magic, but what I want to remind always is that the galaxy is there. You have to mask part of the sky. And working in CMB, for the kind of things that I'll be talking about, this is quite an important thing, okay? And well, this is what WMAP saw. And then, of course, for the first time, we could get a really good estimate of the now super famous CMB angular power spectrum, right? This is the money plot in CMB. And yeah, this is the first one. So with WMAP, with the first data release, when we could start doing this kind of things, again, this is when we started with the era of precision cosmology, right? We could take ΛCDM and estimate parameters with, some pretty decent error bars, okay? And so this was all perfect and a huge success to cosmology for the community. This is amazing. But well, people then, once the data came out, started looking at it a bit closer, right? And started doing, closer analysis or statistically a bit more sophisticated tests beyond just the angular, 2-point correlation function. And people started noticing some weird things in the data, right? I'm just putting some papers here. There are many more. And most of these anomalies happened or seemed to be large scale effects, large angle effects, right? So if you're thinking in multiples, statistically weird things in the low multiples of the CMB. Of course, we'll talk more about large angle anomalies, but when you are at low multiples, large scales, right, you always have the problem of cosmic variance. Statistically, you have to be a bit more careful. And these large angle anomalies, most of them, if not all of them, one of the critique is that, well, they were a posteriori statistic, right? You have the data, you start looking at it, and then you come up with a statistic that happens to be anomalous. You didn't think of that statistic a priori, okay? And so this was some critique. And again, many papers came out. All these papers have plus 800, 900 citations, okay? And this is the one that kickstarted the whole hemispherical power asymmetry thing, okay? It's this paper by Erickson et al., 2004, in which basically what they did is, okay, let me take the CMB sky that WMAP saw, and I'm gonna compute the power spectrum and other statistical quantities in opposing hemispheres of the sky, right? North-south, but also, let me rotate it and take this half and so on. And if the universe is statistically isotropic, if you believe in the cosmological principle, you would say, well, the cosmological information I can extract from this part of the sky should be basically the same within an error bar of the cosmological information I can extract from the other side of the sky, right? What they found is that when computing, in particular, the variance, which is related to the power spectrum, right, is that when you compute the variance in opposing hemispheres, you find that the CMB temperature map, so blue and green dots you can ignore, okay, just focus in the red, yellow shades, and you can see that basically you see a dipole in the variance of the temperature field, okay? I'll give more details now, but this is what hemispherical power asymmetry refers to, okay? Power, because we are looking at variance, hemispherical, asymmetry. Basically, when you compute the variance of the temperature field with CMB, you see a very strong dipole. Now, a few things to remark. I've talked about CMB and that there's a dipole. Please, it's important not to be confused at all, unrelated to the usual CMB dipole, right? The kinematic dipole that whenever you measure the CMB, the first thing you see is a huge dipole that we usually explain due to our kinematic motion, our motion with respect to the rest frame of the universe, right? This dipole that I was just mentioning is the dipole in the variance of the temperature field, not of the temperature. And in fact, I mean, they point in completely different directions. So not the same thing. I said they see a strong dipole. What do I mean by strong? Is that, and we will see this more in detail. When you do simulations of the CMB with, your assumptions of ΛCDM, Gaussianity, anisotropy, very few simulations, about 0.5 or less than 1% of those simulations show such a behavior. Okay.
On what scales do you compute the power?
So to get this, so I mean the hemispheric, this thing refers to just computing the variance in the sense that you don't even go through.
So it's a variance on the scale of the pixel that you were showing.
Okay. Okay. For this plot in this original paper, what they did, it's a bit deceiving. This really, this means that I point to the North Pole here and I divide the sky in two, and I compute the variance in this part of the sky and this part of the sky.
Right, but still you need to define a scale in which you're going to compute the variance.
Yeah. So okay, then I think even in the original paper, yeah, they do. Okay, let me take multiples 2 to 20, 2 to 40, 2 to whatever, and effectively the number of multiples that you include give you this scale, the number of scales that you're including. And yeah, I'm not showing the details, but the thing is, you vary this, let's say, hyperparameters, and the dipole persists. The multiple range that you use, the area, and again, this is the founding paper that then led to the papers in which the hemispherical power asymmetry, as we understand it today, is better defined. And I'll get to that. Okay. So I think I was here, and yeah, so people saw this, and okay, you can either think, okay, this is weird, and there's probably some physics that has to explain it, either of primordial origin, or it can either be local universe physical explanation. I don't know, ISW correlation that you haven't accounted for, or some local mass distribution that's affecting, and you haven't really thought of it. But especially in the WMAP era, this was like, okay, maybe our foreground subtraction technique is not very good, or there's some unknown systematic of the experiments that we haven't accounted for. This is a 1%, 0.5% thing. It's a 2-3 sigma thing. On its own, it's not statistically significant, right? So when people saw this, you could well say, okay, it's there. Is it weird? Maybe, I don't know, but it'll probably go away. Then what happened, that Planck came along, the insignia experiment for the CMB, right? A few years later, it went up and it measured the CMB with better accuracy, fewer uncertainties, longer multiple range, blah, blah, blah. And then soon after, I think the second or third data release came out, then this paper was put out, okay? Power asymmetry and WMAP and Planck temperature sky maps as measured by a local variance estimator. And basically, in this paper, by Akrami et al., what they do is, okay, so you take the sky, okay, and you define little disks, well, little, in different regions of the sky, okay? And what you do is just you calculate the variance in that part of the sky, okay? And again, they did that for both WMAP and Planck, different experiments, different component separation algorithms, in principle, quite different systematics. And what they found is that in both maps, regardless of the radii they use, and again, barring some other artificial hyperparameters, the presence of the dipole seemed to be robust and pointing to the exact same direction. But remember, it's a direction that is completely different from the CMB dipole. This is, okay, so this is a picture that I took from this paper, but there are more. So this is basically, it's a standardized map of what's the variance. Sorry, it's too small, you probably can't see it. This is the standardized variance map for a choice of radii and a choice of number of disks. And here, basically, you can see the histogram, okay? So these histograms here are the dipole in these maps that you measure from simulations, okay, for different radii. And then these are the values you measure for the Planck real data set. And you can see that basically for, regardless of radii, there's only about 1 in 1,000, 2 in 1,000 simulations that show a dipole which is that big. Again, you might be a bit surprised that the values measured of the variance are so different for different radii, but this is related to what Raul was saying, that the greater the disk in which you're measuring the variance, different lengths, so you're getting contributions from different wave modes, and effectively because of the shape of the power spectrum, the variance when measured in areas of different size did not give you the same answer. That's expected, okay? But again, the thing to look at is, well, this is p-value converted to some sigma as a Non-Gaussianity, but well. And the other thing that they looked at is that, well, if you look at the rest of the multiples of this variance map, except for the dipole, which is up here, and the gray points are simulations, okay? So the dipole seems quite anomalous, but the rest of the multiples seem pretty compatible with isotropy. So there's nothing weird going on there. And okay, so this is basically what hemispherical power asymmetry means. And again, as I told you, you can look at this, and on its own, it's a 3 sigma thing. And again, well, I'll talk about that when I get here, but on its own, it's not a challenge to ΛCDM or not. Of course, when this came out, theorists, and coming from the Instituto de Física Teórica, I know that people love to do this, is come up with some explanation for this, both primordial or mostly primordial. They like primordial stuff. Okay, maybe that's what's happening, but I don't know. It's true that when Planck came out and they saw the exact same thing going on, the foreground argument was a bit like, okay, because Planck has 4 different component separation techniques, and regardless of which algorithm you use for map separation, this persists. One of the main arguments for large angle anomalies is the Lucas-Werfing. This is what I was telling you. If I give you a big enough data set, if you look at it close enough, you can find as many anomalous statistics as you want, right? Because it's easy to get the data and then a posteriori start looking at this thing. Yeah, okay, we can discuss this a bit more, and I think there's lots of truth in the look-elsewhere effect. But for example, the same way there is look-elsewhere penalties, if you're familiar with that, when looking at this kind of statistics, I think there should also be look closer rewards. Because for instance, okay, this might not be significant, but let's imagine that in the future we get a full sky polarization survey like Lightbird or I don't know, some other instrument for polarization of the CMB. If I look closer there and I find the exact same kind of dipole, then at which point will you start believing that there's something weird going on and that it's not just, a nitty, a cherry picking statistics that you chose? Again, I'm giving you arguments for this side and that side. The business with large angle anomalies is always complicated, okay? You take your side. Of course, there's always systematics that you have to keep checking, right? I don't know that the beam in the telescope, you assume it to be circular, but it's really not. And coupled with the scanning strategy, then it naturally happens that, the experiment had different sensitivities. And the thing with systematics is that you have to check that your statistic is robust against them, but you can technically never stop, right? There's always things that you could check for. And again, as I was saying, it could just be a statistical fluke. It's a 1 in 1,000 chance or 1 in, 700. It might just be that the universe happened to be that way. End of story. Okay. What I know is that we really don't know if the hemispherical power asymmetry is because of physics, because of systematics, or a statistical fluke. Okay. And people have looked at it for a long time. You can see here, these are the citations to the original paper. The peaks are, of course, related to data releases of, data and people getting more excited. But there are still, 20, 25 papers a year trying to look at this. And basically what we're trying to do with this project is, okay, let's try and look at it closer using some new tools so that we can maybe get a hint of what's going on. And maybe that will help us decide whether, this is clearly systematic or foreground driven, or, well, this particular thing that we're seeing hints towards a more physical explanation. We just need to keep looking. Okay. So hopefully I've conceived what hemispherical power asymmetry is. Now let me jump to the second part, which is, this will be a little break. Okay, will be a bit more statistics oriented, and talk about Minkowski functionals. Okay. People that have worked with Minkowski functionals or no? Okay, perfect. So will be quite a generic introduction. Okay. So in cosmology, we study random fields, right? It could be the CMB temperature, like I was mentioning before, or you can get galaxies and construct your overdensity field, or I don't know, some lensing field or random fields, okay? And usually, since these are thousands or millions of pixels or voxels, data points, we try to extract information from those fields by computing summary statistics, right? This could be the mean, the power spectrum, bispectrum, or some other. You can, it doesn't have to be endpoint functions, but these are, the most typical ones, right? Power spectrum, bispectrum, whatever. But, we know that you can compute this, but of course, they are not capturing the full information of the field, right? Well, that's the whole point. You are trying to compress the information from a big chunk of data to, something more comprehensive. Okay, so Minkowski functionals, MFs, what they do, they are a tool that looks more than the value of the field itself. It's about the geometry and morphology, the shape of the field. And in particular, the field's excursion sets, which I will define in 1 minute, okay? So one of the things about Minkowski functionals is that there are some, functions that are sensitive to, just all endpoint functions. And so you will hear a lot that, Minkowski functionals are used to capture higher order statistics or non-Gaussianity or things that the usual 2-point function is blind to, okay? And another sentence that you might hear usually is that whereas the power spectrum, the mean, or these endpoint functions, care about the strength of fluctuations, how big they are. What Minkowski functionals are trying to describe is what's the shape of these fluctuations. So let's define Minkowski functionals. Let's see how we can do them. So pick your favorite field. Again, CMB temperature, galaxy contrast over density, whatever, defined in some space. So for CMB, this would be a two-dimensional space, a sphere, or if you're looking into galaxy clustering, this would be a three-dimensional space, right? And then you define the excursion set, okay, at some threshold U as the part of the space that lies above this threshold, okay? And you can define this set for any real number U. So from -infinity to infinity, any real number. And then you define the set of your field that lies. It's like, if you have a field, set a threshold, and then you would differentiate between the peaks of the mountains, right? And what lies below the valleys and so on, okay? And okay, here comes the definition. Don't be scared yet. This is the generic definition, okay? For a d-dimensional space, we can define d+1 Minkowski functionals, and they are defined as follows. The first Minkowski functional is it's only giving you what's the volume or the area or hypervolume, depending on the number of dimensions, of this guy here, right? And then the other d Minkowski functionals are defined as follows. Again, it looks very messy. The important things, they are defined with respect to the boundary of the excursion set, okay? And then don't worry too much about this, but this is a symmetric polynomial in the d-1 principal curvatures of the boundary, okay? I had to put this here for completeness, but it'll be much easier than that, okay? Now let me particularize to the case that I'll be interested in, which is the sphere, okay? I know that probably people here would care more if M was R3 or a box, but quite easily generalizable. So when I take M equals the sphere, the three Minkowski functions, okay, remember 2 dimensions, then I get 3 Minkowski functionals. For galaxy over densities and so on, 3 dimensions, I will get 4 Minkowski functionals, okay? And basically, the first Minkowski functional is just what's the area of my excursion set. The first one becomes the perimeter of my excursion set. And then the second Minkowski functional, it's the Euler characteristic. Okay, let me remind you that the Euler characteristic is this topological thing, right? It's not even geometrical, which is basically the number of regions minus the number of holes in my excursion set, okay? This is, in theory, a geometrical quantity. It has curvature, but then there's the Gauss-Bonnet theorem that, well, basically this can interpret it like this. Now, they always say that some image is worth more than some 1,000 words. So imagine this is my CMB, right? And this bar here will denote what's my threshold, okay? And I'll start with a very, very low threshold. And remember, the excursion set is the part of the field that is above this thing. So when I start from the very, very left, all my field is above the threshold, right? So my excursion set is the whole thing, okay? So in this case, I'm plotting V0, right? Which is the area with the excursion set, the normalized area to the total area. So of course, when I start here at the left, very small threshold, I have maximum area, right? As I move the threshold, okay, I'm gonna start throwing away some of the field, right? Because it lies below the threshold. And then the excursion set looks like a group of islands, right? In the CMB case, the hottest spots. Now, of course, the area of all these things relative to the whole area of the sphere is starting to decrease. And of course, when I keep going up and up and up, I'll have less and less and less excursion set. And eventually, this curve goes to 0, right?
Yeah, this is an error function for Gaussian field, no?
Coming. So given a field, just move your threshold, and I've plotted V0, but you can compute also V1 and V2, right? And I'll get 3 curves. The good thing about the Gaussian isotropic case is that we can theoretically predict what's the shape gonna be for this thing, okay? And well, as Raul was saying, for V0, the expected value is just an error function. This is the cumulative distribution function of a Gaussian, right? And you can see that it goes like this, and it goes down. This is the shape of V1 and V2. Remember, V1 is the perimeter of the excursion set. When I start in the beginning, it's the whole thing. There's no boundary, so the perimeter is nothing. Then towards the middle, I have many little islands, like I was showing before. And so the perimeter takes some value. And then again, as I keep increasing the threshold and my excursion set is going towards nothingness, the perimeter is going down, right? And so you expect this kind of behavior. And then this is for the other characteristic, blah, blah, blah. And this is the expected thing. Now, a thing to notice is that for the Gaussian isotropic case, all these 3 curves are characterized by 2 numbers. Okay, U here is the threshold, remember? But the numbers here are sigma and tau. Okay, so in principle for Gaussian isotropic, all 3 Minkowski functional curves in the sphere are characterized by these 2 numbers. What are these 2 numbers? Well, sigma is nothing but the variance of the field. And then this other quantity tau is telling you this is the variance of the gradient, basically. Sigma is telling you how big the typical oscillations are, okay? Whereas tau is telling you how fast the field is changing, whether you're very spiky or you're more smooth, okay? And so these 2 quantities completely characterize the Minkowski functionals of a Gaussian isotropic field, okay? And well, as well, this thing, you can relate it to, this is quite standard, right? You can relate it to the power spectrum, the CLs. And this is an example I'm showing. So the blue dots would be a measured Minkowski functional in some CMB field, right? And this is the V0 prediction, the Gaussian isotropic prediction for a given sigma. This for V1. Well, I haven't plotted the V2, but you can imagine how this goes, right? Something to maybe note, it's not super mega important, but this guy is only dependent on sigma. It doesn't depend on tau, okay? Whereas this guy depends on sigma and tau, this guy depends on sigma and tau. And yeah, it's not, sigma, basically what it's doing is kind of giving you the stretch of these curves. And tau is giving you a bit more the amplitude. Okay.
Yes, you can also predict the variance of this.
For Gaussian isotropics, yes, the full covariance matrix. It's a bit more involved. It's a bit more complicated, but for Gaussian isotropic, yeah, it can be done. Yeah, I'll show a covariance matrix a bit later. Maybe a useful thing. So there's this package, Minkowski, developed by Javier, the postdoc, that is quite easy to use, fairly easy to use, right? So if you have some data set, and it can be CMB, but it can also be you can use this for 3D stuff and so on. And it's a Python wrapper that computes V0, V1, V2, and it has different predictions. I mean, maybe the field you're looking at is not Gaussian, but that's fine. There are other kinds of distributions for which the Minkowski functional curves are known, and this might be something useful. And yeah, just before finishing with the Minkowski functional business, just again, so what's the idea in general? If you're working in the CMB, just you can take a bunch of simulations, run your Minkowski functionals in them, right? And you will get a set of curves. And then you can use them, to look at real data, compute Minkowski functionals, And if you see any significant deviation from the things that you see in the simulations, you can maybe say, okay, there's something going on there. And again, I haven't really gone into detail, but these things are sensitive. So the moment you deviate from this, it's either because you've broken isotropy technically or non-Gaussianity. And these things have been used mostly to, hunt for high order contributions, 3-point or whatnot. So hopefully that was useful. And now I'll jump into the third part. Again, I don't really want to get involved into too many details. So basically, what do we do? How have we investigated further the hemispherical power asymmetry using this thing? So we take Planck data, okay, and a bunch of simulations, okay. Remember, there's always a mask. You have to use it. You shouldn't really be trusting data behind the mask. And okay, so basically, what do we do? Is again, like in the previous references, we put different disks in the sky, different regions in the sky, okay? Of course, since you have a mask, if you put disks uniformly in the sky, there will be some disks in which you're basically fully masked. So we don't consider disks that are heavily within the mask, right? Quite a standard to do that. This is how it would look. Okay, this is what percentage of the area within the disk that we place is covered within the mask. Okay, so you can see, of course, that in the galactic plane, there are many disks that are basically fully masked. So we throw them away. And so out of the 768 pixels on disk we would have, we only keep 606 for quality purposes. And so what do we do? For each disk, we compute the variance, right? With nothing fancy, just you have the value of the field, compute the variance, numpy dot variance. But also compute this tau squared quantity motivated by the appearance of this guy in the Minkowski functionals, which is nothing but the variance of the gradient, okay? And importantly, we compute the 3 Minkowski functional curves that I was talking about in each disk, okay? And so out of each Minkowski functional, what we can then do is fit what's the best fit sigma and tau for that curve, right? So that way we get estimates of sigma and tau directly, but also through fitting the Minkowski functionals, okay? And the good thing about using Minkowski functionals to estimate these things is that then you can compute some sort of goodness of fit, right? You can say, okay, these are the best fit sigma and tau, but how well does the data fit my Gaussian isotropic prediction for Minkowski functionals, okay? And we do this just simply with a chi-square. And what's the idea? So people have always looked at the variance, asymmetry, and so on, just looking at the variance and trying to think whether there's some anisotropic modulation of the field. But but the idea of using Minkowski functionals is, rather than some anisotropic modulation in the universe, is it that there's some Gaussian, non-Gaussian modulation going on? And we hope to look at that. This is an example, for example, take a map, a simulation, and then in each disk, okay, here I'm not showing the disks, but in each pixel we place a disk, compute the Minkowski functional, fit the sigma, and this is, for example, what we would get. Gray is disks that we do not consider because of contamination. And you will, of course, see the first thing that you notice, oh, close to the mask, I'm getting very blue, very low variance. Again, this is related to the thing before. The smaller the area of the disk you're using, because of the power spectrum, you will naturally get a smaller value, right? So this is fine. The only thing is that you have to account for it. You have to correct for it. So what do we do then is, well, for each map of the variance and tau and the goodness of fit, we just standardize it, all right? Subtract the mean in each disk from all simulations, blah, blah, blah. Oh, this got cut. And so basically we get a bunch of, for sigma, we get different maps, estimated from the patch, estimated from the Minkowski Functionals, blah, blah, blah. And yeah, let's just jump into what we see, okay? And yeah, I'll be finishing soon, don't worry. So basically, this is for sigma squared. So we perform, right, the multiple expansion of these variance maps. And basically, the only thing we're doing here is confirm that we reproduce the result in the literature, which is, yeah, there's a dipole in the variance with a similar significance as them. And just the different curves are, maps of the variance obtained using different estimators, directly in the patch, but also when fitting it to V0, V1, and V2. Of course, if one is, these three estimators are measuring the same thing, right? It's, they have some scatter, but they're measuring the same thing. Of course, if you see that one is anomalous, then it is expected to, that the others will, of course, be anomalous as well. But just, checking that we reproduce this and seeing that the p-values are, well, this is 1.3%. In this case, it's a bit lower, but in general, we reproduce that there's a dipole, which is kind of anomalous.
So there's a decent histogram of the 1,000
yes.
Planck
official Planck simulations with noise. Yes.
Okay, so this is L equals 1.
Yes. Yes. This is only the dipole.
Okay.
Okay. So you get this mountain, and then these vertical lines are the Planck, what the real data gives you, and these are the p-values.
And what the disk size are you using? So,
good question. The disk size that we're using, it has a radius of 10 degrees. Okay. But that's our fiducial choice. But we have tested this with disks of radii 6, 8, 12, and 14. Result p-values change. If it's not 1.3, it's 1.2, 1.1, 1.4.
Okay, and as you decrease it further, does it become more compatible with the noise maps?
As you decrease the disk,
you take now 1 at minute.
Yeah. Yeah, I'd have to check because I know we have the results run. I have the numbers in a table, but we still have to look at that. Yeah, because are you worried about something in particular, or the intuition tells you?
I think that because of this look elsewhere effect, I thought a more robust approach would be to take every possible disk aperture and consider the joint distribution of all of them, and then see what is the probability of having n apertures for which you find these p-values. Right, so that would be one thing. But then also, if on small scales you still find this tension, then that would probably point towards a lack of a noise component in your maps. Right? That is not really a large scale. That's not only on large scales, right? It's asymmetry.
So okay, we've done this for the 5, 6 different radii. How would you suggest we having the data that we have on things to assess better the significance then?
Well, I guess you can take the joint distribution of all.
Okay, just combining all the possible.
Yeah, in principle, you have also a covariance matrix for the joint distribution of L equals 1 at 10, 6.
Radii.
So I think that would be good. First, I would remind that there is additional information, so they're not fully correlated. So whatever statistical statement that you make would become stronger. You say, so that maybe you can push beyond the 4 sigma. But I think also would be important to know whether this excess power comes from super small scales or large scales. So then you remind that eventually, if you take very, very tiny disks, then that variance becomes uncorrelated from large scales, and then that should converge to your.
Yeah, I think the usual agreement is that this is coming from low multiple effects. It's not so much about small scale contribution.
Right. So then you should, I guess, converge to a normal value, and I think that would be like a good sanity check.
Okay. Great. So okay, this was for sigma squared, right? Which is again replicating the literature. But now for the first time we say, okay, let's look at this guy, which was the other guy. Okay. So remember, now I don't have 4 lines, I have 3, because the first Minkowski functional is completely insensitive to tau. Remember that? And what do we see? Again, we run the exact same pipeline, okay? And what you see is that, well, the significance is smaller than before, but it's consistently in the 2%, 3% thing. So it's a bit above 2 sigma, 2.4, or so on, which I'll show you a plot now, but okay, this is weird, okay, because in principle, you can, from simulations, you can check in a patch take a Minkowski function, or even with a patch, sigma and tau are quantities that are uncorrelated. Okay, so having a big sigma doesn't mean you will have a big tau, or the opposite.
Oh, well, for Gaussian random fields, they must be correlated.
No. No, if you think of, instead of CL, if you think of C of theta, the variance is C of 0, and the tau basically is the correlation length.
Okay, but I guess once you consider the sigma as a function of scale, then tau is
as a function of scale. I mean, yeah, so, okay, yeah. So, yeah, in the formulas that I showed before, in fact, I can probably flash them back quickly. Yeah, right, do you mean that, yeah, sigma is given by CLs, basically. It goes like LCL, and this is like L cubed CL.
Okay.
So, yeah, there's.
So for Gaussian random fields, you cannot have more information than that contained on CLs, on the CLs, right?
But okay, but the statement that I go to a patch, I compute sigma, and I compute tau, and I do this in many disks in many different simulations, and I plot the histogram, it's almost a perfect circle.
Right, but that's because I guess sigma and tau are sensitive to
different scales.
Different,
this goes like
different L's.
Yeah, this goes like L cubed.
Exactly, and the other goes like L, right? So you are given different weights to the CL. But if you compute sigma for different scales, then you are sensitive to.
Yeah, so you could kind of trace back and infer the tau thing. Yeah. Okay, so we see this with tau, and then we look at. I had these beautiful Greek letters, and then PDF decided to, yeah, okay. And this is the chi-square, because remember, from the fit to the Minkowski functional curves, we can get an estimate of the goodness of fit, again, in each pixel, and you can run the same thing, compute the mean, chi-square, and so on. And again, the significance is 2%, 3%, 5%. Again, this is less significant than the thing before, but there is a dipole in the goodness of fit. And, okay, before I jump into the interesting thing, when you check what are the higher multiples, again, kind of a similar thing. You see that there's a dipole, which is kind of strong, but then the rest of the multiples are quite compatible with the simulations. Same thing here, same thing here, okay? Chi-squared, a big-ish dipole, and then the rest is, let me say in general, Minkowski functionals the first one, the second, the third, and in the galaxy case, the fourth, are sensitive in a different way to non-Gaussianities. It's true that if you pick a random non-Gaussianity, a generic non-Gaussianity, it'll affect, of course, all Minkowski functionals in a similar way. But in principle, they are sensitive in different ways to non-Gaussianity. So Planck seems to be consistent for L bigger than 1.
Sorry, could you go back? So I guess all your statistical statement essentially is the L equal 1, right?
Yes.
That is actually unlikely.
Yes.
But so, and that is I guess 3-ish sigma.
Yes.
But then if you had taken all the first 10 multiples and then you could, so is this distribution incompatible in the sense that now you could say, what is the probability that if I had measured 10 L's, one of them is a 3 sigma?
Yes.
Whereas,
so that's the other thing with the Lucas-Square effect, right? It's why they look at that. And but then in principle, yeah, right, why do I stop at 10? Maybe I take 35 multiples or 2,000 multiples, and then of course it won't be that weird. So the argument there is that, well, you keep the dipole because physically these are very different scales, even from 1 to 2. I mean, okay, 1 to 2, but putting in the same bucket L10 and L1, physically it's a bit like, okay, you're considering physics at 180 degree scales and a physics like this. So should I give the same weight?
Yeah.
But I the first time I heard the argument that, hey, why don't you, of course, it is the same thing. If your data set is big enough, it's normal to see things that are statistically weird. But yeah, we have not computed that. Of course, just by looking at this, you can tell that as you increase more multiples, that significance will come down and down because they seem pretty compatible. But yeah, I mean, still running tests and happy to add more things.
Yes, and this is always the CLs of the variance, right? And
yes, this is for the chi-squared.
Oh, sorry, yeah.
Chi-squared, tau squared for the variance matters.
So I was wondering something, I guess, simpler. So are Planck maps compatible with the Gaussian expectation for the Minkowski functionals? Or yes, not the variance, but the
oh, you mean that to look at the curves themselves for Planck? Yeah. So do you mean?
I mean, are they? I mean, according to your statistics, are they really fully?
So for example, you can look at what's the mean distribution of the chi-squared in the simulations. The value of the chi-squared, and Planck's chi-squared values are compatible with that.
Okay, so it's in the variance, not in the just the amplitude of temperature fluctuations.
Oh, okay, I see.
So you can now these are Minkowski functionals of sigma, right? Let's say what are the Minkowski functionals of temperature?
Oh, yeah. So wait, the Minkowski functionals are of the temperature field. Because that's
okay. Sorry. Yes. Okay.
But that's what you expect to be Gaussian,
right?
And then you fit.
Sorry.
The Gaussian expectation.
Yes.
Okay. Yeah, I understand.
Okay. So. Yeah. Okay. So and then I guess that's what you're computing. I guess with the chi-square, whether these are well described by
the
Gaussian
Gaussian isotropic prediction.
Exactly. Okay.
And again, you can, instead of looking at the multiples of chi-squared, you can, compute the distribution of the chi-squares. Yeah, I'm finishing. And it pretty much looks like a chi-squared. And let's go to the interesting things, perhaps. These are correlations. So because, okay, we are seeing this correlation in tau as well. When you do simulations, so for example, this is the dipole, amplitude of the dipole in sigma, and this is amplitude of the dipole in tau squared. Probably with 1,000 simulations, you cannot say much about things in the tails and so on, but this looks roundish. It definitely doesn't look or the correlation coefficient of this thing is quite close to 0. So yeah, we knew that there was a dipole here. We see a dipole here as well. Again, because of the argument that you were saying, it's just weighting of different scales and so on. You should probably make a more robust estimation of their independence, because you can't just say, oh, their joint p-value is like, but this was interesting to see, because in the simulations, at least when you do this, you see that the dipoles that you measure don't seem to be that correlated. And now, the thing that points to the fact that these things are probably, so blue color, where the dipole in the variance map of sigma points to, just estimated with different things, right? They point in the same direction. Green, dipoles of the tau quantities point here. And this is where the dipoles of the chi-squared maps point. All lying here. This for reference is the direction of the kinematic cycle. Okay. So this is weird. We're still trying to understand a bit, especially, why is chi-squared? Well, it's still work in progress. So you can look at this and say, oh, well, how weird is it? Because maybe it just happens that whenever there's a dipole for variance, there's also a dipole of tau in that direction. So you should look at the clustering. And it's true that there is some clustering, for example, so this is sigma and tau. This is the cosine of their typical distance in cosine. If they were completely independent, the directions, you get a flat line. You don't get a flat line. You do see that there's a certain tendency for clustering. And this is a bit more weird, well, I don't know if weird, but we need to make a conclusion out of this, that the dipole in sigma is usually quite correlated in direction with the dipole in chi-squared. This is for V1, but also for V2. So yeah, let me just now finish, because I definitely went over time. Sorry for that. So basically, we've tried to get a closer look at this whole business of hemispherical power asymmetry, with the idea being, let's try to see if we can learn something new about this. We confirm the variance that was found using different techniques, right? And the new thing is we also look at this tau thing that people had not looked at, and we see that there's a dipole as well, and at least in amplitude from simulation seems to be uncorrelated with the other guy. But again, the important thing, the good thing about using Minkowski Functionals is that you can get an estimate of the goodness of fit to the Gaussian prediction and look at whether there's a non-Gaussian something going on driving what you're saying. And it shows a similar behavior. All dipoles point to the same place in the sky, so there has to be something weird going on. And so to the people doing models to explain this with primordial origin, with some theoretical thing, it could be primordial anisotropy, or maybe the thing that's driving this variance asymmetry is some non-Gaussian contribution, but we need to keep checking. So yeah, 2 minutes to 11. I'll put it here, and I'll be very happy to keep discussing with you. Thanks.
Thank you very much for the great talk, Mikel. So first of all, are there questions online? Like, unmute yourself and ask. You have questions?
I guess it is no work this way. Well, I guess one needs to raise like the hand online. Because we didn't set up the Zoom, so I think it's working a little different. But
like it's a VIPC Zoom, so
yeah, but it's not like everybody can just speak, I guess. So if you're online, you can raise the hand, and maybe then Mikel can see this on the laptop.
Yeah.
I think I also can.
Yeah, I can see the chat, and I can see that there's 4 participants.
Well, the chat is deactivated.
Wow.
Well, I can't even see who's joining, so I'm just joining with the link that we send around.
All right, if you have questions,
But-
maybe you can ask in Slack. And,
Yeah, that would be fine. I'm looking there.
yeah. And if not, maybe people here, we can ask Mikel over the coffee. And
Yeah, coffee sounds great.
so if there is no questions online, let's thank
I don't
Mikel
see
again.
any. Yeah, but this advantage if you don't set up. We don't have the full control over it.
Yeah, but using like the DIPC Zoom, people could like unmute themselves.
Yeah, now you should connect with her phone. And then she was on Moritz. Oh, Moritz is.
Yeah.
Right.
Oh, yeah, I met her.
Yeah.
So, stop.
Yeah.
Especially right.
Yeah, but she would make herself,
Host.
make herself host on with her phone. And then.
She didn't pay the Zoom.
No.
I'm taking the place.
You're taking the
Now
place,
it's short.
but it's coffee time.
Yeah, it's coffee time, but we had to. I mean, usually we do a 10 shift, but we had to shift at 11. I think that you booked faster than us.
What time? Okay, so
Yeah,
Sorry.
but I booked like last week. I think the last month. Hemos quitado.
Variedad. ¿Cambiar el ordenador? O
Su Windows mi sta schierando. Aveva un server, mi sta spannare il server. 10 secondi.
hai preso qualche dato?
Sì,
Ieri?
sì, questa mattina. E non capisco perché. Se faccio in OR viene un spettro così vicino a se faccio in ANGULO viene altre tipo maggiori.
Perché forse ce l'hai troppo alto.
Ha mandato quel filtro, il primo picco.
No, ma mo la risposta è sbagliata. Consigliate il domani.
Però in realtà questo mi sono sbagliato più tipo il storie mie soltanto il pugno gigante si
Ma quello più che altro bisogna vedere il primo delle il vantaggio strano, il vantaggio basso. E poi bisogna pure se quello che so, cioè che fare un botto io.
Can you check if I'm on the right Zoom link? Yeah.
Did you get it from Slack?
Yes, I took the last one from the group. I think that nobody is. So
Right, there's your name.
Anche in test così mi arrivano le attenzioni. Blocca le connessioni uscite. Sì, lui è stato nel... You are in the red room. Whenever you want, you can start.
okay. Okay, so voilà. Okay, so good morning. So update on GAP today. So last time we spoke about sensitivity to low energy event with yes, sensitivity to low energy events in xenon and argon. We spoke about the first scan of the S2 yield, and we spoke about the detection threshold study. So I will give an update on all of that today. So first I want to start by speaking about the detection threshold because I think that it affects all the next results. So here I explain how I did the analysis. So I'm doing an exponential fitting in this range, so 0,2. So I decided to take 0,2 because when we increase the electroluminescence field, we have a population here at low energy that modify the detection threshold. So we need to take it in account. So then I defined the threshold like this. So it's just the integral of this exponential, and with this probability value that is fixed at 0.001. So it's the probability of presence of noise above this threshold that you see here. And then I defined the error like this. So then last time you saw this plot with the black curve and this blue curve, and I added so the detection threshold from the real data, so with the analysis. So all the points are taken from the analysis except this one because the value was a bit crazy, so I had to adjust it in another way. So the main thing for this plot is to show that we are sensitive to energy below 1 keV. So this is the main information that we want to show here. And now I want to speak about what is degrading the detection threshold. So last time I said that when we increase the yield field, so we have this population, as I said, that increases. But we also have another thing. So here you see two sets of data at 4.5 bar. So the left and the right are the same configuration, except for the voltage in the PMTs. And the thing that we want to see here is that here at low energy, you see that we have a clear decrease of noise when we decrease the voltage in the PMTs. So we see it for 3 configuration. And here, so what you see is I did, so all the histograms are normalized, and I did the sum of the counts in this yellow window. And so I did the plot here, and we see that for 1.2 kV, it's the presence of noise is higher than 1.1. So yes, and also the 2 data sets here I taken not on the same day. So I also wanted to check what happens if we do this check on the same day. So here it's 3 times the same configuration. I just changed the voltage in the PMTs, and we also see this population that is increasing. So as conclusion, we are sensitive to low energy events with real data. And also, so we are producing noise with intense electroluminescence field and the voltage in the PMT. So future improvement is to define a detection threshold more realistic and to select a data set that is more optimized. So which means where the detection threshold is the lowest possible for the paper. So now I want to speak about the S2 yield. So this is the tree plot of last time. And in fact, we see a spread here of the lines, and in theory, it's supposed to be everything overlapped, so one straight line. So we wanted to check the slope again with a 1.2 kV in the PMTs. So it seems that it's not really better. But yes, it's like this. And yes, also have this shift yesterday in the data at 8.5 bar that you see here. So for now, we don't know why we have this thing. I have to investigate. But we think that something happened with the PMTs.
The resolution, sorry, is 15% at which energy?
Sorry?
The resolution at which energy? The iron?
The 5.9 kV peak. 5.9.
5.9, okay.
And here also, so I wanted to test different methods in order to improve this analysis. So in fact, the 4 methods, they do the same thing. They localize the peak in photoelectrons, and then we fit with the 5.9, I mean, we convert in kV and we do the fit and so on. And so I tried the 4 method and I see the same results 4 times. So it was also the opportunity to do a cross-check just to show that this spread is not due to bad analysis, but it's due to physics. So I tried to make a list on what can create this spread. So as we said, we have noise at low energy due to PMT's voltage and intense EL field. So it can produce extra charges that can affect our yield. And also, so far we don't take in account in the analysis, but that can also affect the yield. So I'll show you an example. For example, here we have this 4.11 kV peak, and here we also have a 6.5 kV peak here. And so if we don't take them in account in the analysis, so maybe it can create this spread that we see. So yes, one improvement is to include more processes in the analysis and to update the calibration value in order to check the fitting value with the literature. And now another improvement on the energy spectrum. So the goal was to align the energy over time in order to increase the statistics. And so this time I used an interpolation. So here you see before and after the alignment for the same method. And here it's the result that I obtained for a run of argon that was not stable. So in blue, it's the spectrum before the alignment, and in yellow, in orange, the spectrum after. So we see a gain of amplitude in both, so this 5.9 kV peak and this 2.9 kV peak. And we also see a reduction of the sigma value because the peak is more thin. So yes, conclusion. So with this method, we improve the sensitivity to low energy events for argon. We don't need it because it's already pretty stable. And yes, in the future, we need to make some runs with argon using a lowered voltage in the PMTs in order to reduce this range that represents the noise and maybe to see better the peak at low energy. And yes, one last thing, I started to work on the gap giant force simulation. So I want to use it in order to fully understand what are all the contributions each time in the energy spectrum. So I'm analyzing the true Monte Carlo data. So here you see it. So I did the sum of the energy deposition for each event. So this is why we have some direct peak. And then in order to simulate the resolution, the energy resolution of the detector, I apply the smearing. So as what I described here, and this is the result that I obtained. And now I need to investigate more on the study of the output and so on.
Why do you have a continuum below 5 kV, even without any smearing or things?
Speak about this?
No, on the left plot.
Oh.
Yes, there is a continuum.
Yeah, I don't know. This is why I need to study it more.
Okay.
And yes, so for the gap simulation, I need to improve the simulation, so some geometry to fix some bug, and also to study more the output to understand well each contributions. And yes, I finished by the planning of data taking, so calibration of the PMTs for 1.1 and 1.2 kV, and make new scan and long runs of argon with a lower voltage in the PMTs. So that's it. Thanks. Questions?
Yeah, I have one.
Yes.
In the slides of the alignment,
Sorry.
This one, did you use cosmics to the next one? Sorry, the previous one. Did you use cosmics to calibrate the alignment?
No.
What did you use?
So this represents also it's in photoelectron, sorry.
Okay.
Yeah. So this is the 5.9 kV peak, and I do the alignment with this one.
Okay.
Well, as a suggestion, try to explain it with a bit more calm, because for people that are not familiar with the analysis or with the detector, it's a bit difficult to follow. And then for the simulation, how do you simulate the relative intensity of the various peaks?
Relative, like you mean?
Like why one peak is higher than the other one?
Here you mean? For example?
Yeah, or the 2.9, for example.
So I generate a ion source that, well, I have to check for the process, but it's supposed to, just the classic decay. And now I have to check the ratio to see if everything is going well. So yes, the different amplitudes are due to the fact that we are more or less producing some, I mean, it depends on the probability to produce some.
So you're simulating the entire chain, you're saying?
I have to check, but I think yes.
Okay. And then how did you apply so that is the sigma you get from your data?
Yes, so I take the sigma of this peak, and then yes, I take all the energy deposition and I apply this Gaussian with a mean at 1 and the standard deviation calculating with this calculation.
Yeah. And have you tried to overlay this with the data?
No, not yet.
Okay.
Can you repeat again what's the difference between these two plots?
So it's just the smearing.
Okay. And have you looked at the one on the left in logarithmic scale?
Sorry?
Have you looked at the one on the left?
Yes. I mean, I don't have it here, but yes, that's right.
Any questions? Everyone, for the aluminum, the X-rays of the aluminum, they are produced from the iron impinging on an aluminum target in GEANT, or you are simulating them from another thing?
No, I'm trying to add like in reality a foil of aluminum and
in front of the iron source.
Yes,
and
but
GEANT manage the production.
I'm not sure. And in fact, I also have some problem with depending on the way I position my vertex. So it's also something I need to understand. So for now, I cannot really simulate the exact configuration because of that.
Okay. Other questions? Okay. If not, the next speaker can go.
Yes. It looks like. The last one. Thanks. Yes, no. Let's go and stop here. And then I multiply by this regular.
Okay, so my talk is basically an application topology in next experiment. So first of all, as a quick recap, the main goal of the next experiment is to look for the neutron star beta decay in xenon 136 in a gas. And then NX 100 is basically the latest detector of the next collaboration. So basically, all my talks during the last months have been about topological studies, which basically try to discriminate between signal events and background events. As we have a double beta decay, a signal event is just an event which has 2 electrons, and therefore when these electrons propagate in the gas, they will end up in 2 big energy positions, which we call blobs. And background events only have 1 electron, so we will only have 1 blob, and that's how I wanted to discriminate between them. So until this point, my method was basically just to apply a kernel density estimation, and with that, try to find the blob centers. Today I'm going to show that that's not enough by itself, and we have to do some improvements for that. So as a quick review, with the kernel density estimation, I could try to do this kind of 3D images and try to find the blob centers. To do this, what I was doing was trying to implement the KD in 2 dimensions in the 3 projections, the ZX, ZY, and XY, and doing the mean between the coordinates I was including. And with these 3 projections, I could also reconstruct in 3D. Basically, the blob center was considered to be the region where the probability of finding a hit, which is given by the kernel density estimation, was maximum. So the actual projection like this, which is ZY, and the ZX, we have the density for this kind of tracks, which is quite elongated, and we can see only 2 blobs and a quite a straight path. We can clearly see just 2 maximum. So in this case, everything works okay, and we can really discriminate between the 2 peaks. The problem here comes when we do not have that kind of tracks. For example, I moved on to Monte Carlo simulations, and in this kind of track, where the blue is a true track, we see we have this secondary track here, which leads to a higher energy position, and therefore a high probability of finding a charge deposition in the detector. So if we went again to this ZX projection, what I will see is this higher peak in the middle, which corresponds to the secondary track, that doesn't correspond to the actual electron track. So therefore, I will identify a blob here and maybe another blob here, and I will say I have 2 blobs, but these are not the actual blobs of the event. So we need to try to improve the method a bit to find the real blobs and not fake blobs. So what we know so far is that with the KD, I can try to find the probability of finding an energy deposition, and with that method, I can estimate the blob center. But